Additive manufacturing is digital technology. New and perfect parts are produced in a fast and efficient way by combining a digital data description with an advanced material processing algorithm. Additive manufacturing is gaining speed in replacing old ways of manufacturing. But it needs to move faster to become a real game changer. Sooner rather than later.
Additive manufacturing now can really outcompete the traditional technology. So the whole industry is at the tipping point.
What we compete with, what we want to challenge, is casting and forging. And those are 6,000-year-old businesses. It's time to replace them with something more modern that can lighten things, that can make them stronger and make them, well, more environmentally friendly.
Freemelt 1 is an open source system, which means that the users can develop parameters without any restrictions. Their creativity is their only limit.
Electron beam powder bed fusion is a fantastic candidate to lead the transformation of manufacturing. But it can't be done without the right tools. Freemelt has developed the algorithms to release the full potential of this technology. We have packaged them into a very powerful data preparation tool. Now we are ready to talk about it. Imagine that you are free to decide the material properties in the part you produce. Now imagine that you can do that selectively in every different place in that part. This magic is possible with our 3D printing technology solution, where each individual spot is melted, one after the other. Spot melting. Melting one small area at a time, pixel by pixel, is what we call pixel melt. The high-power electron beam is focused on a tiny area of the powder bed, a pixel. As a result, the powder in a small volume in that area is melted in a fraction of a millisecond. The melted powder re-solidifies to form a new small fraction of the final solid part. Meanwhile, the electron beam has moved to a different position to repeat the process. This takes place again and again at an incredible pace, leading to the successful addition of a new build layer in seconds. Sequential melting, jumping between different locations, enables material control down to the resolution of the electron beam in our 3D printing systems. Our new software tool controls all the relevant parameters to select the material structure locally, everywhere in your part, to suit your application.
Freemelt 1 is today used in many material labs around the world together with pixel melt.
Very few people think about designing material properties to really optimize a part, both when it comes to the shape of it, but also to the material properties. If you can merge that, then you have a superb product.
In Freemelt 1, we use unique magnetic coil technology to form and position the beam. This empowers the full potential of pixel melt processing.
Pixel Melt is a cloud-based software tool, so it can run from any computer. The heavy calculations for the algorithms are done in the cloud. In Pixel Melt, there are many spot melting algorithms to choose from to influence the material, and we will continue to add more options. Here you can see printing with a few of the options, both ordered and randomized melting sequences. Vastly different spot melting strategies can be applied to the same melting layer by dividing the area to be melted into subsections and applying different spot melting algorithms to the different sections.
In Pixel Melt, we process sliced 3MF data. When creating a new project, we can either choose to upload a new file, or we can choose one that's already been uploaded. Our geometry of interest today consists of 6 20 by 20 millimeter in diameter test bars. We'll choose this file now. Now we'll also give the project a name. In this case, 3 by 2 cylinders, which would be apt. We'll also make sure that we transform this to make sure that it's centered on the build plate. Lastly, we'll also add a note to the project, describing what intended material we're using. In this case, TI64. The 3MF file that we've chosen contains 6 separate objects, This means that we can also partition this file into 6 separate partitions. We'll do this now. And why? Because we want to attain more granular control of our parameter set. Our project contains only one partition, the model itself. What we'll do now is that we'll also partition this based on the number of objects inside. Partitioning the model in this manner gives us the ability to choose, as stated previously, unique parameters for each object. Now that we got all of that setup sorted, we can go ahead and create our project. Now that we've created our project, we are presented with the editor. This is where we can choose our beam parameters, our mesh parameters, as well as our spot spread algorithms and our dwell time algorithms that we can use in a project. In the editor, we can choose to work on one partition, several partitions, or all partitions simultaneously. For this build, we've chosen to vary our dwell times while keeping the other parameters constant. Thus, we choose the following: spot size 200 microns, beam power 900 watts, mesh size 200 microns. And for our spot spread algorithm, we've chosen single directional shifted, which is an ordered algorithm. And for our dwell time algorithms, we've chosen a constant dwell time varying throughout our 6 partitions from 175 microseconds to 200 microseconds. Next, we'll navigate to the left-hand side of the screen, to the Build tab. Here, we'll choose the path to our project. We'll choose the initial temperature, the preheating and the post-heating repetitions, as well as the layer feed parameters. We choose the following parameters: initial temperature 610 Celsius, preheating and post-heating repetitions 50, recoating parameters, layer thickness of 50 microns, and a recoating speed of 80 millimeters a second. Now we click the Generate button. Once the generation is complete, the build files, together with their accompanying build script, as well as a single image that's been generated for each generated layer, will be available for download.
Before we start printing, we take several steps to make sure that our printing process goes accordingly. So the first thing we do is fill up our powder tank and our build tank with a certain amount of powder. We set up our start plate that we align with the recoater system. After that, we close the chambers and we put the vacuum in it. Once we have done this, we go to Boki, and there we lower first the start plate by a certain amount of distance, because we're going to be building at high temperatures, and this is to avoid the rake scratching the plate because of the thermal expansion. After that, we warm up the plate to the desired build temperature, and then we heat up our pro-heat plate because we're going to use it for the preheating step of the printing process. Once this is completed, we lift up the plate, and I already have a script that does this for me, but the users can decide whether or not they want to lift the plate with a script or manually themselves. Once this is completed, we can start printing.